Universe, Dr. Rachel Livermore.
So thank you very much. I'm very excited to have been invited to speak to you all today. I think if we can find a way to combine astronomy and sex, we'll be laughing. For now, I'm just going to focus on the astronomy. As you can probably tell, I'm from England. I came to America just over a year ago. I drive a pickup truck, and I've learned to say y'all unironically, so I'm expecting my green card any day now. Thanks. So I'm going to be taking you right to the edge of the universe. My work focuses on the most distant galaxies, which we see so far away now that the light from them has taken almost the entire age of the universe to reach us. This means we're looking back in time, obviously the further away we look into space, and with new telescopes and new surveys, we're now probing right to the edge. So that's what we're going to do. We're going to dive right in, and we're traveling away from the Milky Way, many, many, many times the speed of light. What you're looking at is galaxies, all of them. Every single point you see on this screen has hundreds of billions of stars in it. And as we go further away, you see that the galaxies change. We've lost all our nice spirals and pretty shapes. They've gone bluer. Blue galaxies tend to mean they've got more young stars. So this is when stars were forming really, really quickly. We're over halfway back to the Big Bang now. You can see that they're all a lot smaller. They're irregular. Part of this effect is just that obviously as we go further away our resolution isn't as good, but also galaxies are intrinsically smaller. They're starting to build up their stellar mass. And as we go further away still, you see they're not as blue as they were. They're starting to get a bit green. And this is one of the things I'm going to talk about. The fact that the universe is expanding means that the light from them becomes redder. So slightly redder than blue is green, trust me on that. And here they're now starting to look a bit orange. And if we get all the way to the back, these are the things that I study. They're tiny, tiny little red points. These are the very first galaxies that formed in the universe. And this is what's going to teach us about how our own galaxy, the Milky Way, came to be. So here we are now back at the Big Bang. There's nothing, there's no light, no stars and galaxies are formed. So that's my talk. I thought I'd just for the sake of it, I'm just going to preempt the first question. So I just stated as fact how far away these galaxies were. And in fact, to make that movie, I had to plug in a distance for each one of those galaxies and then fly through them. So how do I actually know? This is a really non-trivial question because we can't just go out with our tape measure. We can't plot it on Google Maps. Measuring distances to things in space is really one of the biggest challenges that we face as astronomers. And the reason we can do this is basically all down to one person. This is Henrietta Leavitt. This image was very kindly donated by our next speaker, Haley. So I'm pre-advertising her talk in advance. Henrietta Leavitt, my favorite scientist of all time, did all of the courses required for a BS in physics, was not allowed to be awarded a degree because she's female. But she worked at Harvard, and her job was just cataloging stars and measuring how bright they were. The way this was done at the time, this was just photographic plates, right? We didn't have digital cameras. So they had these things that kind of called like fly swatters, that had different sized holes in them. And they would hold this fly swatter over an image of a star and measure how big the star looked, and that was its magnitude. Amazingly, actually pretty accurate. They hold up pretty well. The type of star she worked on was called a Cepheid variable, and you can see images of these at the top of this picture. They're called Cepheid variables because they vary, and they get brighter and dimmer over time. Those of you who can see the bottom of the screen, there's a little graph of the brightness as a function of time. It just looks a bit like a sine wave. It's up and down. They actually don't look much like a sine wave. I think it's a bit of artistic license. Now, the reason this was a really important discovery was that she noticed something about them that no one else noticed. And this just was because she was studying this all the time. When you do something, even if it's something really menial and repetitive all the time, you notice things that other people don't. What she noticed was that there was a very clean relationship between how quickly these stars varied and how bright they were. So the brighter stars take longer to reach peak brightness in each one of their cycles. All of the stars that she was studying were in the Magellanic Cloud. Any of you who have been to the southern hemisphere may have seen this in the sky. It's the most distant object you can see with the naked eye. It's actually a separate tiny galaxy that's in orbit about the Milky Way. The reason that's important is that means all of these stars were at the same distance from us. So the ones that she saw as brighter were actually brighter. They weren't just closer. So this is a really important relationship. It's very easy to measure how quickly something gets brighter and dimmer, much easier than it is to measure how far away it is. So this is how we calibrate distance. This work was done in 1912. Shortly afterwards, it was put to good use by Edwin Hubble, who studied this galaxy, Andromeda. Now, if you have really, really, really good eyes and are in a really, really dark sky site, then this is the most distant object you can see with the naked eye. Personally, I've never managed it. This is our closest large galaxy. It's of order the same size as the Milky Way, and it's 2.5 million light years away. Well, we didn't know that in the 1920s. Extragalactic science, what I work on, is a really, really new field. So Edwin Hubble, who now has a telescope named after him that you may have heard of, looked at this galaxy and found some of these Cepheid variables in it. And by calibrating this scale, measuring how quickly these Cepheid variables brightened and dimmed, he was able to measure the distance to Andromeda. This was a huge deal because at the time, no one knew how big the universe was, and there was this huge argument between people who thought that the Milky Way was it, and people who thought the Milky Way was just one of many galaxies. People had seen images like this for a long time, but had no idea what they were. It was completely reasonable to say that this was a star with a gas disk around it. In fact, it's billions of stars, hundreds of billions of stars. But how do you know if you don't know how far away it is? So Hubble measured the distance to this as 900,000 light years. The Milky Way is about 100,000 light years, so this was enough to put it way outside the Milky Way and tell us that our galaxy was an island universe, as they were called at the time. In fact, that measurement was wrong. It's actually like 2.5 million light years. But if you're dealing with people who work on the very distant universe, that is an amazing estimate. Frankly, I'm very happy if I get things within a factor of 10. So this is what gave birth to extragalactic science. It also told us that the universe is expanding. And I want to dwell on this a little bit because a lot of people get very confused about this idea. If all the galaxies are moving away from us, you might think that we're at some kind of privileged position in the universe. We're at the center and everything's moving away. In fact, this isn't quite how it works. When Hubble discovered that all galaxies were moving away from us, actually Andromeda, the one I just showed, is the exception that's moving towards us. Apart from that, everything's moving away from us. And the further away something is, the faster it's moving. And this is evidence that the universe is expanding. And the best analogy for this is that of a balloon. If you take a balloon and you draw galaxies on the surface of it, you inflate the balloon, all of those galaxies move away from all the other galaxies. So you can pick any one galaxy as your center, every other galaxy is going to move further away from it, and the further away they were to start with, the faster they'll move. And this is true whichever one you pick as your center. Now this works because the universe, in our balloon analogy, is just the surface of a balloon, which is two-dimensional. You then have to wrap your brain around how you convert that into a three-dimensional balloon surface in some kind of four-dimensional space. Don't bother. No one can do that. Just imagine the universe is a two-dimensional surface of a balloon. You're good. So the reason the expansion of the universe is really important to us is it changes light. If everything appears to be moving away from us, it's not really. The space in between is getting bigger, but it's the same as far as we're concerned. This means that light, as it travels towards us, is going to be changed in the same way as sound does with the Doppler effect. We call this redshift because everything's moving away from us, the light moves to the red. In this diagram here, we've got the Earth on this side. This is where we're looking at some galaxy over on the right-hand side. In the top, we see this black line here in the green. So if that galaxy was green, it's completely stationary with respect to us, it looks green. If you start that galaxy off moving away from us, those light rays are going to be stretched out, and it will become redder. So you can see it's moving now through the spectrum into this yellow bit. If the galaxy was moving towards us, the reverse would happen. This line shifts slightly towards the blue end. This doesn't really happen with galaxies. Everything's moving away from us, so we call it redshift. The light from them is being redshifted. So this brings me on to my summary of the entirety of astronomy. What we're concerned with is studying light, is what we study. And there is a lot more to light than meets the eye. Haha. So all we can see with our eyes is what we call optical light. That's represented on this chart by this little rainbow here. That's everything we can see with our eyes. But if we stretch it out, this is wavelengths of light. This bit here, a bit less than a micrometer, is our visible light. There's way more than that. We can get to higher energies, so this is smaller wavelengths, and we get into things like gamma rays and X-rays. And what this plot's actually showing us is how much of that gets through the atmosphere. You can see this black line here shows us that everything at this high energy end is blocked by the atmosphere. This is very good for us. We wouldn't last very long if there were gamma rays and X-rays bombarding us every day. But it also means we can't study that type of light in space unless we go up to space ourselves. So to study gamma and X-rays, we have satellites in orbit around the Earth. Things like GALEX, XMM Newton, and Chandra study the very high energy light, which is not what I work on. If we move into the optical, this gets through the atmosphere, so we can do this from the ground, which is awesome. This image here, if those of you can see it, I've tried to keep all of my slides in the top half, because I know how annoying it is being in here and not being able to see over people's heads. But sorry, this is one exception. In the optical, we can use telescopes on the ground. This image here is the summit of Mauna Kea in Hawaii. This is the site of most of the best telescopes in the world because it's one of the best sites in the world for doing astronomy. It's very high above the ground, it's very dark, and also, kind of counterintuitively for Hawaii, very, very dry. And this is important to us because water in the atmosphere messes up our images. Even at the top of a mountain in Hawaii, though, our images aren't perfect. The atmosphere does all kinds of weird things to distort them. So we still go up into space, even to study the optical, hence the Hubble Space Telescope. If we move further along into higher wavelengths, you can see this atmospheric transmission line gets kind of jumpy. We've got a few discrete bands in there that we can observe from the ground, and we do. Some of those telescopes on the summit of Mauna Kea do actually observe a little bit into the infrared. But if we go further out into the infrared, again, we have to go to space. Our best infrared telescopes at the moment are Spitzer, which is very old now, and Herschel, which has just finished its mission that was launched in 2009. We then get out here in the sub-millimeter, which means just less than a millimeter. But if we get out to the radio, again, we can do this from the ground. So we have radio telescopes. There's a big one in New Mexico, just up the road. America's kind of big. It's actually quite far. The great thing about radio is the wavelength's really long, so you can combine lots and lots of dishes together, spaced quite far apart, and this can act as though it's one gigantic telescope. So that's why you see things like the Very Large Array, the one in New Mexico, which was used in the film Contact, is acting as though it's one gigantic telescope, which is really kind of awesome. So that is my summary of the entirety of astronomy. And what I'm hoping to demonstrate to you is that color is really, really important. A lot of people think we make color images just because they look pretty, but it's actually most of the work that I do is using the colors that we get from images. And the way we make color images is we have to take multiple images of the same thing at slightly different wavelengths. So the same way your computer or your TV does it, it has a red, a green, and a blue image, and it combines them to make it color. So this afternoon, just for fun, I downloaded 3 images from the Hubble Space Telescope archive of, this is the Whirlpool Galaxy M51. These are just the names of the filters. All you need to know is this one's blue, this is green, this is red. These are actually all roughly in the optical range of the spectrum. This one is actually probably slightly redder than our eyes can see, but it's close enough. Now, you can see immediately, just by looking at these three separate images, that they're slightly different. The first two is kind of difficult to tell the difference, but if the reddest one, it's quite noticeable that this bulge in the center is a lot brighter, as is this little companion that's sitting next to the main galaxy. This becomes a lot more noticeable if you combine the images and make them color. And I have to say, when I made this image this afternoon, it's made me want to cry. Because, I mean, you're going to see some of my galaxies, the really distant ones, they're not as pretty as this. This is pretty amazing. So this is what the Whirlpool Galaxy looks like in color, and I don't know how good the projector is, if you can actually make out the colors. But what you should be able to see is in these spiral arms, lots of blue things, and then lots of red fuzziness. That's my technical terminology. What the red is showing you is basically dust. You have lots of hot new stars being formed in this spiral disk. This is heating up any gas and dust in the disk. And this gas and dust is then re-radiating that light at longer, redder wavelengths, and this makes these regions look red. So these red areas are where new stars are being formed. And in the center, you can see this is a bit orange. That's because there are lots of older stars in the center of the galaxy. So all the work that I do really depends on the way that hydrogen affects the colors of galaxies. To first order, you can basically say the universe is made of hydrogen. Job done. See, chemistry's easy. So when the Big Bang happened, lots of protons and electrons were fused together and made lots of different elements, but basically everything was left as hydrogen. It's about 75% just after the Big Bang, and it's still about that today. You've got new elements being fused in the centers of stars, but as far as I'm concerned, they're negligible. So all I care about is hydrogen. This is my very classy PowerPoint demonstration of a hydrogen atom, cut in half because space. And the center, we have a proton, and those rings going around it are our electron shells. So this is a bit of a classical picture of the atom, but it does us well enough. These are the different shells in which the electron can orbit. We number them 1, 2, and 3, imaginative. And we're going to plonk our electron in the second shell. This means it's a little bit excited. It's on a higher energy level. At some point, it gets bored of being excited, and it will drop back down. And this will emit a photon, a bit of energy, and it will have a very, very specific energy, wavelength, frequency, all interchangeable when it comes to light. So that 126 nanometers, that's the wavelength of the light that's going to be emitted when the electron does that little jump. And that's in the ultraviolet. It's a bit bluer than our eyes can actually see. There are a few, in fact, that it does in the optical range of the spectrum. The other really useful one that I use, we're going to plonk another electron. When I made this slide, I really should have deleted the first electron first. Let's pretend I haven't put 2 electrons on a hydrogen atom. So we now have an electron on the third energy shell. We're going to drop this one back down to the second energy state, rather, and this is going to give off a photon at 656 nanometers. So this is in a region we can see. It will look red to our eyes. And that's why that image I just showed you of M51, all those little red splotches in the spiral arms, they look red because they're giving off that particular signature of hydrogen, which is pretty cool. So the reason hydrogen's so important to me is mostly that first transition. So you've got a distant galaxy, and at the bottom here, this is the Hubble Space Telescope that's trying to observe that galaxy. Unfortunately, the universe is not empty. Unfortunately, I mean, it's good, it made us. But there's lots of stuff that we don't necessarily want in there, and most of that stuff, as I keep saying, is hydrogen. So we have a big cloud of hydrogen gas here, which is purple in my universe. And we're going to trace some light that's leaving that distant galaxy and traveling towards the Hubble Space Telescope so that we can see it. Now you can see that our red light and our green light get through perfectly fine and will be observed on our telescope, But our blue light goes, oh, hello, it's a hydrogen atom there. You would like this 126 nanometer photon I've just given you, wouldn't you? And the hydrogen gas goes, yes, please, I would. But now I'm bored of being excited. I'm going to shoot it off in this direction. And another hydrogen atom picks it up and shoots it off in another direction. And we call this scattering. And if you think I'm dumbing this down too much, this is pretty much exactly how I explained it in a professional talk last week. So this blue light here, which we're imagining is basically anything blueward of 126 nanometers here, is going to be shot off in random directions, and so we're not actually going to see very much of it. And this gives us what we call a Lyman break. Lyman alpha is the name of this particular photon that's given off here. That's the jump from the second to the first energy level in hydrogen. And this signature, where we see this red and this green, but not this blue light, is called a Lyman break. And this is what it looks like in a real galaxy. At the top, we have my cartoony representation of what filters are available on the Hubble Space Telescope. These regions here are the light that's being let through as a function of wavelength. These four here, there are actually more than this, but these are the ones that I use in the survey that I work on. These four here are in the optical range of the spectrum. This is on an instrument called the Advanced Camera for Surveys, ACS, on the Hubble Space Telescope. And then these three here are my favorites. These are in the near infrared on a new camera called the Wide Field Camera 3, WFC3, which was just installed on the Hubble Space Telescope in 2009. Now, the reason I love those filters and that particular instrument is it looks in the infrared, which means that if we go to very, very distant galaxies, that Lyman break I just showed you, the light that's being captured by hydrogen between us and the galaxies, shifts redder and redder and redder, and it ends up outside of the visible range of the spectrum. So when we look at, this is a galaxy that's it's over 90% of the way back to the Big Bang. We see nothing in these four images. These are the four optical images, nothing. So if you just looked in the optical region of the spectrum, you would say that there are no galaxies that far away. Once we add in this new infrared instrument, there's suddenly this booming signal here. And I should mention that astronomers quite often do this thing where we reverse images, so black means bright and white means not bright. The reason for that is it saves printer ink. Seriously? So what you're seeing here, this black splodge, is a real thing. That's a galaxy. And we don't see it here because all of the light that would be given off in this region has been absorbed by hydrogen. So what this is telling us is we need to look in the infrared if we want to detect distant galaxies. And this has actually only really been possible on large scales very recently, since 2009 when that camera was installed. One of the first things that camera did was take an image called the Hubble Ultra Deep Field. And I still think that this is the most incredible image ever taken by mankind. It was taken by focusing the Hubble Space Telescope on one region of sky for 11.5 days. The telescope is basically a bucket for light. Two ways of collecting more rain in a bucket: you get a bigger bucket or you leave it outside for longer. We don't have the option yet of putting a bigger telescope in space, but we can leave it pointing at one thing for a really long time. And in 11.5 days of pointing at, this is a region of sky the same size as if you took a drinking straw and looked through it. That's how big that entire image actually takes up on the sky. There are about 10,000 galaxies in it. So, I mean, I'm not going to do the math live on stage, but if you can multiply up how many drinking straws you can fit across the entire sky times 10,000 galaxies, that's pretty much how many galaxies are in the universe that we can detect in 11.5 days with the Hubble Space Telescope, which is pretty amazing, but it's a really, really tiny area. So the project that I've been working on since I came to Texas is called CANDLES, which stands for the Cosmic Assembly Near-Infrared Deep Extragalactic Legacy Survey. I didn't think I'd remember that. So, thank you. So astronomers are kind of renowned for having these really, really terrible acronyms. And I'm actually quite grateful that this one is a misspelled word, because normally they're just words, and you try and Google them. And So the great thing about the CANDLE survey, it's actually studied 5 fields. 2 of them are useful to me because of the types of filters we observe them with. They're called GOODS North and GOODS South. Really imaginative, I know. And GOODS, oh, that's an acronym too. Great Observatories Origins Deep Survey, possibly. I may have made that up. But one's in the north and one's in the south. There is a reason they're slightly different colors. You can see the one on the right is bluer. That's because when I made these images quickly this afternoon, I had to use a slightly bluer image for the blue band in this color image because the bluest of the infrared images, are you following me, doesn't cover this region and it looked a bit rubbish. This image here actually is in the same location as the ultra-deep field that I just showed you. The ultra-deep field fits about there-ish. I did that by eye. It's close enough. So these 2 fields together cover 50 times the area of just that ultra-deep field. It's not quite as deep, but it's pretty good. And so this gives us a lot more information about these distant galaxies. So if I take that off, what I'm going to show you is the distant galaxies that we found in these fields, which isn't published yet. So I'm really excited to be able to show you this. These galaxies here are 93% of the way back to the Big Bang. So we're getting back pretty far now. You'll notice that they are kind of clustered in some regions. That bit there that is the Hubble Ultra Deep Field I just showed you. That image is a bit deeper, so therefore we can find more. There's also some strips here where we find nothing. That's because one of the really important filters is missing from those regions of the field. Other than that, they're fairly uniform, give or take a little bit. So I said this is 93% of the way back to the Big Bang. Let's try 94%. We get a few more. 95%. And now we've hit our limit. Once we go more than 95% of the way back to the Big Bang, that Lyman break moves even outside of the infrared filters, so we just don't see anything. So this is really our limit. 95% of the way back to the Big Bang, only 5% to go, we're nearly there. But of course, these are only candidates. I've presented this Lyman break technique as though it's infallible. It's not. There are actually closer galaxies that can kind of mimic the colors of very distant galaxies. And the only way we can really confirm it is to take spectra. This means we take the light from a galaxy, we disperse it into all its component wavelengths, and we look for that really distinctive spike, that 126 nanometers that's coming from the hydrogen within the galaxy. And we can do that, but it's really slow. It takes at least, we're finding 12 to 18 hours per galaxy just to confirm one. We're fortunate that we have some instruments now where we can do multiple galaxies at once, but it's still pretty slow going. This I like to show just for fun is the Keck telescope in Hawaii. This is where we do this work. I'm working on this one here on the left, pointing my beam into the sky in one position all night while the one next door is going crazy and looking at lots of different stuff. So the laser, incidentally, is how we correct for atmospheric distortion. I like to call it the death ray. You feel really powerful when they let you play with that. So how did we do with the Keck telescope? We've been pretty lucky at getting time on it. It's very competitive. And we've done really well. We actually had the most distant confirmed galaxy ever. I say we. My boss did this just before I arrived in the States. It was actually published just after I arrived. You may have seen it in the news, things like this, most distant galaxy yet. And look at that beautiful picture. Isn't that amazing? It's not real. I mean, this one is cheating quite a lot. If you look at the actual image of the galaxy, I believe that's an artist's representation. Yeah, it does say that. It's a bit... if you look at the actual image of the galaxy, it looks like that. I told you mine are not as pretty as M51. It's a tiny little red splodge, and the reason it's red is we only detect it in the very reddest filter, so we can't make up a pretty color image of it. The spectrum that we got from Keck, I want to show you this just so you can see what actual astronomical data is like. It's pretty ugly. Look at that. So what you're looking at is the light that's been dispersed into different wavelengths, and this is how much light we're getting as a function of wavelength. It's all over the place because there's a lot of noise. I mean, the things we're looking at are really, really faint. So we're limited by mostly sky background. In the near infrared, the sky gives off all sorts of emission that we don't like. All these spiky bits here are from the sky. You might be able to make out there's a squiggly line at the bottom. This is just measuring sky, so you can see which bits of wavelength to completely ignore. If you look at the top, this is the two-dimensional spectrum. What we do is we slit
Universe, Dr. Rachel Livermore.
So thank you very much. I'm very excited to have been invited to speak to you all today. I think if we can find a way to combine astronomy and sex, we'll be laughing. For now, I'm just going to focus on
Universe, Dr. Rachel Livermore.
So thank you very much. I'm very excited to have been invited to speak to you all today.